All right, so today we're going to talk about global maxima and minima. We've talked about local maxima and minima, and now we're going to talk about global maxima and minima. And as you might expect, a global maximum is just, out of all the possible maximum points, which one is the biggest, right? Which one is the biggest? We're going to choose the one, or there might be more than one at the same maximum. Same way with a minimum, we're going to look at all the candidates for the minimum and just compare them and figure out which one's the smallest. So there's a couple different situations we might be looking at, depending on whether we are looking at the function on a closed interval or not. So if we have a closed interval, then we have to look at the local maxima and minima and also the endpoints to figure out what the overall global maximum or minimum is. Okay, so you can see in this illustration here on the left, even though we have our local minima and our local maximum, the points at the end are actually bigger than our local maximum. So we have to consider those when we're choosing the global maximum. Okay. Now, on the right here, we have a situation where we don't have a closed interval, and then we have to look at the overall function. So you can see this maximum, we have a local maximum here in the middle, but it's not the global maximum. In fact, the function goes off to infinity in either as x goes to positive or negative infinity. So there really is no global maximum, okay, because it just goes off forever. All right. So let's take a look at example 1. Now this is the same polynomial function that we've been working with in the last 2 sections. And so we really already know the critical points. We've done this before, right? To find the critical points, we're going to take the derivative and set it equal to 0 and find the critical points and then evaluate them either by the first or second derivative test to find out whether they're a local maximum or a minimum. So since we've already done this, I sort of just wrote it out here for you. Okay, we take the first derivative and set it equal to 0, and we find that the critical points are at -2 and 8. And then I used the second derivative test. So I took the second derivative, just taking the derivative of the derivative, and then evaluate the function at those 2 points, -2 and 8. Now when I evaluate the second derivative at -2, I got -30, which means that it's concave down, right? So it's concave down. I always like to draw a picture. Concave down looks like upside down U, right? So that means that the point where it's equal to 0, the derivative is equal to 0, has to be a maximum. Okay, so we can say that there's a local maximum at x equals -2. The same way with 8. When I evaluate the second derivative at 8, I get 30, meaning it's concave up, which means so the function is concave up, so we have to have a local minimum at x equals 8. All right, so we did that before. So the thing we need to do now, though, is look at all the possible points and evaluate the function at each one of those points and determine which one is the global maximum and what's the global minimum. Well, we have to keep in mind that we have this interval. It's on an interval. The interval is from -5 to 14. Okay, so we're limited there. So let's do that. Let's evaluate each one of those points. We have to evaluate -5 and 14 as well as the two critical points. Okay, so I'm just going to evaluate the function. I'm going to evaluate the function at -5 first, just because it's the smallest. I'll do them in order. All right, so that's the left-hand side of the interval. And if I put that into the function, I'm going to put that into the original function. All right, so I'm going to compute -5 cubed minus 9 times -5 squared minus 48 times -5 plus 52. And when I evaluate that, I got a -58. Okay, so I'm just going to keep doing that. I'm going to do my critical points here. I'm at -2 and 8. And then I'm also going to evaluate the function at 14 because that's the other endpoint. All right. Now, so I went ahead and did that. Just plug the numbers into the original formula, the original function, f of x. And when I plug in -2, I got 104. When I plug in 8, I got a -396. When I plug in 14, I get 360. Okay, just plugging it into the original equation. So now I can just compare all of those points and figure out which one is the global maximum, which is the global minimum. All right, so the global maximum is the biggest one of these, right? So it looks like 360 is the biggest one of all of these. Global maximum is 360. That's the value of the function. And at the point, x equals 14, right? And then we need to evaluate the global minimum. So we look at all of these points and figure out which one's the smallest. It looks like it's a -396. So that's the smallest function value. And that occurs at x equals 8, right? So that's my answer. Those are the global maximum and minimum. All right. So I'll meet you in the next video for the next example.